What specific problem does the TR-DPO method aim to solve in the context of large language models alignment?
The TR-DPO method aims to solve the problem of static reference models during training in the context of large language models alignment. Specifically, the traditional direct preference optimization (DPO) approach keeps the reference model fixed, even when new data with human preferences becomes available. This static reference model limitation can hinder the alignment process, as the updated policy may diverge from the original reference model, impacting the model's performance. TR-DPO introduces a novel approach by dynamically updating the reference policy during training, either through a soft integration or outright replacement with the updated policy. This method allows for more adaptive alignment, ensuring that the model stays closer to the most relevant reference model as it learns from new data. By addressing the issue of static reference models, TR-DPO enhances the effectiveness and adaptability of alignment algorithms for large language models.
How does the TR-DPO method work? Illustrate step by step.
The TR-DPO method works by updating the reference policy during training in two primary ways: soft update and hard update. 1. Soft update. This method involves gradually merging the current policy with the reference policy at each training step using a weighting factor, alpha, which determines the rate of influence on the reference policy. Both the current policy pi_theta and the reference policy pi_ref are initialized from the same parameters. The soft update allows for incremental adjustments to the reference policy, ensuring that the trained policy remains close to the reference policy. 2. Hard update. In contrast, the hard update method involves directly substituting the reference model with the updated policy after a specified number of training iterations, denoted by tau. This approach leads to more significant and episodic adjustments to the reference policy, promoting larger jumps in the model's learning trajectory. The choice of alpha and tau values in TR-DPO is crucial for determining the frequency and magnitude of updates to the reference policy. A small alpha or large tau results in rare reference policy updates, keeping the trained policy close to the reference policy, similar to DPO training with alpha equals 0 or tau equals infinity. On the other hand, a large alpha or small tau leads to frequent updates, allowing the policy to move further away from the reference policy, as measured by the KL divergence, akin to a pure trust region set up with alpha equals 1 or tau equals 1. Overall, TR-DPO provides a flexible framework for updating the reference policy during training, balancing between stability and adaptability to improve model performance and alignment with human preferences.
What are the theoretical or practical benefits of using TR-DPO over traditional DPO for alignment algorithms in natural language processing?
The theoretical and practical benefits of using Trust Region Direct Preference Optimization (TR-DPO) over traditional Direct Preference Optimization (DPO) for alignment algorithms in natural language processing (NLP) are significant. The introduction of TR-DPO allows for the dynamic updating of the reference policy during training, either through a soft integration or outright replacement with the current policy. This adaptive approach ensures that the model can continuously adjust to new data and preferences, leading to improved alignment with human-centric metrics such as coherence, correctness, level of detail, helpfulness, and harmlessness. TR-DPO outperforms traditional DPO in model pair comparisons, showing a 19% higher win rate for the Pythia 2.8b model. Additionally, TR-DPO demonstrates superior performance across different model sizes and natural language generation tasks, as validated on the Anthropic HH dataset. The method effectively balances alignment with generative diversity, managing long text generation more efficiently. Furthermore, TR-DPO's update strategies, both soft and hard, enhance model performance on various datasets, as confirmed by GPT and reward model evaluations. The method's adaptability across different model sizes and tasks, with careful parameter tuning, highlights its potential to optimize outcomes in NLP applications. Overall, TR-DPO offers a more flexible and effective approach to training language models, leading to improved model output quality and alignment with human preferences compared to traditional DPO methods.
How was the efficacy of TR-DPO tested and validated across different natural language generation tasks and model sizes?
The efficacy of TR-DPO was tested and validated across different natural language generation tasks and model sizes by introducing the TR-DPO method and comparing it to the traditional DPO approach. Specifically, in model pair comparisons using GPT-4, TR-DPO with an alpha of 0.6 showed a 19% higher win rate than DPO for the Pythia 2.8b model. This method's effectiveness was tested across 2 natural language generation tasks and 4 different model sizes. The probability of improvement (POI) metric was employed to demonstrate that TR-DPO statistically significantly outperforms DPO in key human-centric metrics such as coherence, correctness, level of detail, helpfulness, and harmlessness, specifically validated on the Anthropic HH dataset. Additionally, the impact of various alpha and tau settings on generation diversity was analyzed, revealing a high correlation between KL divergence and generation length. This analysis confirmed that TR-DPO effectively manages long text generation, showcasing its efficacy across different tasks and model sizes.
What were the key results achieved with TR-DPO in terms of performance metrics and model comparisons?
The key results achieved with TR-DPO in terms of performance metrics and model comparisons include the following. 1. TR-DPO outperformed the traditional DPO method, showing a 19% higher win rate for the Pythia 2.8b model in model pair comparisons using GPT-4. 2. TR-DPO demonstrated statistically significant improvements in human-centric metrics, such as coherence, correctness, level of detail, helpfulness, and harmlessness when compared to DPO, specifically validated on the Anthropic HH dataset. 3. The analysis of various alpha and tau settings showed a high correlation between KL divergence and generation length, indicating that TR-DPO effectively managed long text generation. 4. The experiments confirmed that both the soft update strategy, TR-DPO-alpha, and the hard update strategy, TR-DPO-tau, enhanced performance compared to the traditional DPO approach on the Anthropic HH and Reddit TLDR datasets for the Pythia 2.8b model size. 5. TR-DPO with alpha values between 0.5 and 0.7 consistently outperformed higher alpha values and the baseline DPO, while gains with TR-DPO-tau became more significant as tau increased from 32 to 512. 6. The POI metric analysis across absolute human-centric metrics confirmed that TR-DPO statistically outperformed the DPO baseline, enhancing dialogue quality as measured by coherence, correctness, level of detail, helpfulness, and harmlessness. 7. The evaluations revealed an optimal performance range for TR-DPO-alpha around alpha equals 0.5 to 0.6 and for TR-DPO-tau at tau equals 256 and 512 across different datasets. 8. TR-DPO showed potential to enhance model performance across various model sizes, from 410M to 12B, with careful parameter tuning being crucial for achieving an equilibrium between adherence to the SFT policy and adaptability for effective adaptation. 9. The analysis of generation diversity showed that updating the reference policy influenced KL divergence, length, self-blue scores, and rewards, with a nuanced trade-off between alignment with human preferences and generative diversity. 10. The gradient dynamics analysis indicated that a balanced choice of alpha and tau in TR-DPO resulted in better convergence by moderating the frequency and scale of policy updates, ensuring a stable trajectory toward optimal policy refinement.
What are the limitations or potential drawbacks of the TR-DPO method based on the findings presented in the paper?
The limitations or potential drawbacks of the TR-DPO method based on the findings presented in the paper include the risk of performance degradation when using excessively high alpha values, such as alpha equals 0, 9 and very low tau settings 2, 4, 8, 16. These extreme parameter values can lead to deviations from the supervised fine-tuned SFT policy and result in repetitive word generation, impacting the quality of the model's output. Additionally, the paper highlights the importance of precise calibration of alpha and tau to achieve a balance between adherence to the SFT policy and the adaptability necessary for effective adaptation. Furthermore, the TR-DPO method may face challenges in maintaining stability during training, as indicated by the potential for increased gradient scales with higher alpha values in soft updates and lower tau values in hard updates, which could lead to training instability and degradation in model performance. Therefore, careful parameter tuning and consideration of the specific model and task at hand are crucial to mitigate these limitations and optimize the effectiveness of the TR-DPO method.